All right, so I've started the recording, so we're officially in session. Oops, I've got the note showing here. I wanted to show the, instead I wanted to show the, but you're familiar with this. So this is just the list of homework assignments that are due, right? So these two are due before the test. So these are really important. Practicing with the first derivative test, right, to find critical numbers and then determine if critical numbers result in turning points, right, either a local maximum or a local minimum. That process is called the first derivative test, right? And then if you carry out just exactly the same process but with the second derivative, that's how you can find inflection points and where a function is concave up or concave down, right? So it's an identical process. A second derivative test is an identical process to the first derivative test, except it's carried out with the second derivative, right? And it deals with, and of course, it tells you about concavity instead of function direction, which is what increasing or decreasing, which is what the first derivative test tells you about, right? So if you look at the sample test, there are several problems about the first derivative and the second derivative test, right? So make sure that that you're able to do those things on Tuesday for sure, right? That will be a big part of the test, and then do at the same time as the test. Actually, you can continue working on these homeworks while you're doing the test. Are these homeworks about anti-differentiation, right? Finding antiderivatives. These are the basic problems in this homework about finding antiderivatives, and we're going to talk more about that today, and then also Tuesday as well. And then this integration by substitution technique, which is a more complicated way, right, of which is a way of dealing with more complicated antiderivatives. We started practicing that last time, but we have several more examples to do with the so-called integration by substitution, which is actually that's actually kind of the reverse of the chain rule, right? Chain rule is a rule for finding derivatives, and then integration by substitution is sort of inverting the chain rule to find anti-derivatives. Okay. All right. So those are the homeworks and the sequence, right? That before the test on Tuesday. And then we have this one other. This is an optional homework, so this is strictly up to you if you want to mess with that. And then we have this one other homework that's due at the when the final, on the day that the final will be turned in. Which also deals with antiderivatives, okay, but an application of antiderivatives. All right. So here's practice finding antiderivatives, and then here's an actual, these problems involve what you can do with antiderivatives once you have found them, okay? But this is not covered until the final exam. So now on your review, I will, on the review, I'm working on the solution, so I'll have the solutions ready sometime this afternoon, so I'll post those this afternoon or this evening. I will send an email when those are posted. And but now the video for the review, I will not do that until tomorrow, so that will not be ready until tomorrow sometime. So I'll work on that tomorrow morning, and then hopefully by tomorrow afternoon I'll have that in YouTube, uploaded to YouTube. So that's kind of how that's kind of how the schedule is going to work, right, between now and Tuesday. And then don't forget, on Monday at noon, Madison has her review for the test number 3. So I strongly encourage you to attend Madison's review to help you prepare for test number 3. And then I think it would help you to take a look at the review video that I make as well, okay, because I might be stressing problems on that review that I know are on the test, right, or that are important for the test. So if you look at the video review that may that I make, that may give you hints on what what really to look for on test number 3, okay, when it's posted. Yeah, Damien, it's 12 noon is when the Madison's test review is. Okay, so I think that was for people who took the makeup test for test number 2. I think that was really helpful. Those of you who went to Madison's review, I think that really helped. So I think if you go to her review for test number 3, that will also be really improve your score. And she will also have a final exam review, but we'll talk about that on Tuesday, and she'll be posting information about that later as well. Okay. So, but for now, just concentrate on getting through test number 3. Okay. Are there you guys? All right. So I just said a lot. Do you guys have any questions about either what I just said or other things that you wanted to ask me about before we launch into the notes here for today? Okay, so as usual, right? If you have questions, if questions occur to you during the lecture, then let me know. If I don't see the chat, you may have to. If you ask it in chat and I don't see it, you may have to yell at me because it's hard for me to pay attention to the chat and also pay attention to my notes. But anyway, okay, so I think I said all the important things that I needed to say. So I want to. We're going to go to the notes now. So let me switch to that. And let me scroll down here for a second because I inserted a problem. If these are the right notes, yeah. I inserted a problem that Colin asked me about earlier today. This is from that homework on the first derivative test. So that's due tonight. Oh, I forgot to mention, right? That first derivative homework is due tonight, right? So try to get that done by midnight. And so I don't know which number this is, and your problem may look slightly different, but the question was, here's a function. They're using the variable t instead of the variable x. So t is our second favorite input variable, right? Because we often use that to represent time in some in some practical application. I don't know what the application of this function is. I think you're just given a formula, and so here's a formula for a function, and all you want to find are the critical numbers. So you're not asked to do anything with the critical numbers. So you're not going to use the critical numbers here to find to locate the possible turning points or to test if those turning points are actually authentic turning points, right? We just want to find the critical numbers and that's it. And so we know, right, that we find them by finding the first derivative and then setting that to 0, but also looking for where the first derivative is undefined, right? Because that also can be, those also can be critical numbers. But that's a little bit more unusual situation, right? The sort of the standard type of critical number would be where the first derivative is 0. So so let's just do that here because this is just results in some interesting algebra. So so first, of course, to find the critical numbers, we have to find the first derivative, right? So so you've got to be skilled at finding first derivatives now, and but y'all are very good at that, right? So let's find the derivative here, and this is going to involve using the product rule. So this derivative is a little bit more complicated because here we have the product of these two expressions, right? T and square root of 13 minus t. So we're going to find the derivative by using the product rule. All right, so let's recall the product rule, right? In the product rule, you're going to find the derivative of the first expression, which in this case is t, and then multiply it by, keep the second expression, right? Which here is square root of 13 minus t. Well, the derivative of t is 1. That's so easy. So you have 1 times the square root of 13 minus t. Okay, so that part was not hard, right? And then plus, and now the second half here is a little bit more difficult. First, you just keep the t now, right? So you're alternating derivatives, right? So you keep the t, but then you have to find the derivative of square root of 13 minus t. All right, so that we may have to think about a little bit. I want to find the derivative, so I'm going to refer to that as d over dt of this expression, which is square root of 13 minus t. You may wonder about this notation that I'm using to indicate the derivative of this expression, right? See, you might have written this function formula. Instead of using f of t, you might have written y equals t times the square root of 13 minus t, right? And then, of course, then notice, right, that you can write the derivative here as dy over dt. So that derivative notation you're very familiar with, correct? But what I've done here, since I didn't really introduce or use the variable y in the original problem, instead of writing dy over dt, what I did was just substitute square root of 13 minus t for the y, right? Because that's what y is equal to, right? I'm sorry, that's not what y is equal to. Darn it, confusing you guys. All right. We're trying to find the derivative of square root of 13 minus t. I could have thought of square root of 13 minus t as, I could have written it using this equation, right? Y equals square root of 13 minus t. And then dy dt would be the derivative of square root of 13 minus t. But instead of writing the y, I just directly wrote square root of 13 minus t. So that's how that notation means derivative. All right, now, all right, so that was all just kind of miscellaneous comment there. All right, so, but now how do I find the derivative of square root of 13 minus t? Well, I'm going to have to write that using a fractional exponent, right? So I'll write that as 13 minus t to the 1/2 power. So I want to find the derivative of 13 minus t to the 1/2 power. And now y'all know how to do that very well, right? You just bring down the 1/2. We're going to use the power rule, right? Bring down the 1/2. So you have 1/2 times 13 minus t to the minus 1/2 power, because you have to subtract 1 from the 1/2. And it's very tempting to stop there, but you cannot stop there because you have to multiply in now the derivative of 13 minus t, right? That is the chain rule. Now, if this were t minus 13, the derivative of that would be 1. But this is 13 minus t, so the derivative is negative 1. So that's kind of a little catch here in computing this derivative. The derivative of 13 minus t is not positive 1, it's negative 1. So you have to multiply this by a minus 1. Let's see, what does all that simplify to? Well, if you convert the minus 1/2 back to a radical, that's a negative exponent, so it's going to go into the denominator, right? So you end up with minus 1 over 2 times the square root of 13 minus t. So that's the derivative of square root of 13 minus t. It's minus 1 over 2 times the square root of 13 minus t. Let's plug that in now. So you have minus, I didn't write that right. So you have minus 1 over 2 times the square root of 13 minus t. Wow, so see, that was already a lot of work there, right? And we haven't even really got into the problem, because remember, what we're trying to do is find the critical numbers. And so we find those by setting this to 0. So we end up with an equation that we have to solve. It's square root of 13 minus t. Now it's going to be negative minus, let's see, what do we have here? T over 2 times the square root of 13 minus t equal 0. Wow, now we have left with a formidable algebra problem here, or it looks kind of formidable anyway. We have to solve this equation. right? Wow. You guys have any suggestions on how I can start solving that equation? It's going to come out with a weird number solution, but what would be the first step in solving this equation? What would y'all like to do here to solve this? Any suggestions there? When you're solving a what now, Damien?
I was gonna say set them equal to each other.
Yeah, so that would be one thing, Lance, right? You could just bring this term over to the right-hand side. I think that's what you're suggesting. And then you would have square root of 13 minus t is equal to positive. That's a little bit better. At least we have a plus there instead of a minus, right? So we had positive t over 2 times the square root of 13 minus t, okay? And all right, so that maybe looks a little bit better. Any suggestions now for step 2?
Square to get rid of the roots.
Square both sides? Yeah, all right, so there's a good idea, okay? So you could square both sides, and that would be a perfectly legitimate way to go here, all right? I have another suggestion, though, okay, which is kind of the same as squaring both sides, all right? I'm going to multiply both sides by square root of 13 minus t, okay? So that's kind of equivalent to, not quite the same, but kind of equivalent to squaring both sides. So I'm going to multiply both sides by the same quantity. Remember, you can multiply both sides of an equation by the same quantity as long as it's not 0. So I'm going to multiply both sides by the square root of 13 minus t. And the reason I did that is because I sort of looked ahead and saw something good's going to happen. These cancel, right? So I get rid of the denominator. And then when you multiply a square root times itself, of course, what happens to the square root?
It cancels out.
Yeah, it cancels. So you would just get on the left-hand side, you would just get 13 minus t. So you see this, now this looks a lot easier, right? Okay. So that's looking a lot better and something that I could solve a lot more easily. Now I just solved that by, let's pull the minus t back over to the right-hand side. So I have 13 is equal to t over 2 plus t. And if you have half of t and you add a t to it, that gives you 3/2 t. So here we just have 3/2 t on the right-hand side. And now you can get rid of the 3/2 by multiplying both sides by 2/3, which is the reciprocal of 3/2. So multiply both sides by 2/3, and you get 26/3. What a weird number, is equal to t. So you get kind of an unusual critical number there, but we don't care what the value is particularly, right? There it is. So there's our critical number. So, you know, that involved a little bit of algebra, but the process is what's important, okay? So that's what you really have to recall, right? If I'm looking for critical numbers, that's kind of the first step of the first derivative test. Remember, the first derivative test is a little bit more involved than just this, right? But the first step of the first derivative test is you've got to find the critical numbers, right? And you do that by setting the derivative to 0, okay? So I think the first few homework problems on that homework that's due tonight are just going to say, find the critical numbers. So that just means find the derivative, set it to 0 and solve, and then also think about where the first derivative is not defined. Because in some unusual instances, you may get critical numbers where the first derivative is undefined. Remember, it's the first derivative undefined, but the original function has to be defined at that number. So you can't have a critical number at some value that's not in the domain of the original function. Okay. So, all right. So just wanted to go through, that's probably the hardest problem you're going to encounter in finding critical numbers. I think the ones on the sample review are not as hard as this one. Okay. All right. So do you have does that jog any questions there about something from the homework? All right. And now last time we were talking about integration by substitution, But that's a little bit, again, that's a little bit more complex process for finding integration. And you're going to practice that a lot for those people who are taking Calculus 2. You're going to do a lot of integration by substitution. In fact, like 80% of the course is a lot of integration by substitution. But so we're going to come back to some examples, but I want to look at just some easier examples of integration where you don't have to do something as fancy as integration by substitution to find the antiderivative. Okay. All right. So let's start with here, right? So remember, if you're just given this expression where you have the integral sign, right, and then this integrand, that's the expression inside the integral, and then of course the standard dx here at the end. You know, what you're being asked for is to compute an antiderivative, right? Okay, so if you're given this on a test, you'll know sort of, oh, I'm supposed to find the antiderivative here, right? Now, we know how to find antiderivatives of powers of x. That's, it's kind of the only thing we know how to find antiderivatives actually when we start learning how to find antiderivatives is finding antiderivatives of powers of x. And this is a power of x. You just have to write it in the correct form, right? So you have a cube root, and you can write that as a power of x, and it's in a denominator, but that's okay. We can get it out of the denominator, right, by using a negative power of x. So if you convert this to a power of x, you can rewrite the integrand here, the quantity after the integral sign, as 2 times x to the minus 1/3 power. All right, so y'all have done that a lot you've done that process a lot, right, of rewriting expressions using negative exponents when you're finding derivatives. Same thing's going to happen when you're trying to find antiderivatives, right? You have to rewrite roots as exponents, right? Okay, now, so what we have here, we immediately recognize is a power of x, right? You have x to the minus 1/3 power. So that we're going to be able to integrate using the anti-power rule, the opposite of the power rule, right? The power rule is what we use to find derivatives of powers of x. The anti-power rule is what we use to find antiderivatives of powers of x. The one thing that's a little bit ugly here, though, that's kind of in my way is the 2, because this is not just completely a power of x, because it's got this coefficient of 2. So that's a little bit troublesome, right? But that coefficient of 2 is not going to stop us at all. Just like it wouldn't stop us if we were trying to find the derivative, it's not going to stop us in trying to find the antiderivative. That coefficient really is kind of meaningless to the problem. Let me show you how we can sort of make it meaningless. One of the nice things about integrals is if you have a constant, it's got to be a constant, not a variable. If you have a constant behind the integral sign, you can always factor that in front of the integral sign. So you can bring constants from inside the integral sign to outside the integral sign. And that's really useful in integration. Okay, so really the 2 here, I can just sort of not completely ignore it, but sort of make it, not problematic in integrating here just by factoring it in front of the integral. And now what I'm really integrating is not the 2, because the 2 is outside here, right? Okay, now what I'm integrating is just a power of x. And we integrate powers of x by using the anti-power rule. So we know the antiderivative here is going to be x to the minus 1/3, right, plus 1, divided by minus 1/3 plus, right? Okay, it's the opposite process from the power rule. Instead of subtracting 1 from the exponent, you're going to add 1 to the exponent. Instead of bringing the exponent down and multiplying, you're going to divide by the new exponent. Make sure you divide by the new exponent, not just minus 1/3, but the new exponent, minus 1/3 plus 1. And see, the 2 is just hanging around here, right? Because the 2 is outside of the antiderivative. So the antiderivative really is this fraction. And then since we had this antiderivative multiplied by 2, we have to multiply our answer here also by 2. And then don't forget, as always, add on that arbitrary constant at the end. So the rest of this now is just arithmetic or algebra. You've now found the antiderivative, right? The integral sign is gone. So this really is the antiderivative. It just looks kind of messy here. We can make it a little bit cleaner. Let's see, this is 2 times x to the what? 2/3 power, right? Divided by 2/3 plus this constant. And now when you divide by 2/3, that's the same as multiplying by the reciprocal, 3/2. So you have 2 times 3/2, and then x to the 2/3 power, we can convert that back to a radical. That's going to be the cube root of x squared. The 3 tells us that we have a cube root, right? And the 2 just stays as an exponent. Plus a constant. Here the 2's will divide out. So we end up with what? 3 times the cube root of x squared plus a constant. So there is our antiderivative. So apparently, I'm not going to spend the time doing it here, but you could check this. If you take the derivative of this expression, ultimately, after you've done simplification, you will end up with, if we did this right at least, you will end up with 2 over cube root of x, right? So if you take the derivative of this, you're going to get the integrand that we started with, okay? All right, so see that very nice thing I wanted to illustrate here? If you have a constant, not a variable, a constant in an integrand behind an integral sign, you can factor it in front of the integral sign. And you cannot do that with a variable. It's so tempting to do it with a variable sometimes. Okay, so sometimes you'll have an x in your integrand, and you really don't want it there for some reason, and it's very tempting to think you can factor it in front of the integral sign. Unfortunately, you cannot. That only works for constants. All right, I'm going to save this example for a little bit later. We're going to come back to it. Let's look at C now. So I claim I can do this integration without using substitution. This is not a integration by substitution problem, but it looks really hard, okay? Because I have this fraction here, right? X cubed minus 3 over x squared. And that's not just a power of x. You know, x cubed is just a power of x, right? But that's not just a power of x. That is, you know, because it's got an x squared here in the denominator. So that looks like, not sure what to do with that, right? Okay, and you're going to find out that actually in many cases, integrating fractions like this, where you have x's in the numerator and x's in the denominator, sometimes those are really hard, okay? But, and there are lots of fancy techniques that we can use to integrate fractions like this one. But this one, fortunately, turns out to be kind of easy, because what I'm going to do is I can break this fraction up. Since I only have x squared in the denominator, fortunately, I don't have x squared plus 1 or, you know, x squared minus 3, or I just have x squared by itself in the denominator. I can break this fraction up into 2 fractions. So I can write this as x cubed over x squared minus 3 over x squared. See, if you added these 2 fractions back together, since they both have the same denominator, you could just combine them with the common denominator, right? So you could write what we had here, x cubed minus 3 over x squared. So, so these 2 things are the same. But now that's convenient, though, in this case, to break the fraction up. Sometimes not convenient to break a fraction up like this, but here it is, because we can rewrite these fractions. X cubed over x squared, that just reduces to x. And minus 3 over x squared, I can write that as minus 3 times x to the minus 2 power, right? See this x squared in the denominator? I can write that as a minus 2 power. So look, what we really have here, we didn't realize it at first, what we really have here are just powers of x. This is x to the first power, and this is x to the minus 2 power with that extra 3 there. All right, but if we sort of ignore the 3 for a moment, what we have are just powers of x. And we know how to integrate powers of x because we can do that using the anti-power rule. So we have hope here of finding this antiderivative. Now, here's the second thing I have to notice. When you have antiderivative of a sum or a difference like this one, sum or a difference, not product, sum or difference, you can break that up into the sum or difference of different antiderivatives. So in other words, I can write this as the antiderivative of x minus the antiderivative of 3x to the minus 2. So I can integrate this term by term. Now, if this were x times 3x squared, you could not break it up like this. But since it's x times minus 3x to the minus 2, I can break this up into two different antiderivatives. Now, guys, so this one I think is pretty easy. What can we do with the 3 now? That's a constant. So what did I just say? When you're having an integram with a constant in it, what can you do with the constant?
Bring it in front.
Bring it in front, right. So this is really antiderivative of x minus 3 times the antiderivative of x to the minus 2 power. I'm going to run myself out of room here, but that's good because we're almost finished. All right, Van, now you really definitely see all we have are powers of x. This is x to the first power, and this is x to the minus 2 power, right? Okay, because we factored the 3 out, we don't have the 3 here by the x to the minus 2 power. So we just have powers of x. And powers of x we can integrate using the anti-power rule. So what's the antiderivative of x? So what is the anti-power? This is x to the first power, right? So what does the antiderivative say what does the anti-power rule say you do with that? What are we going to get here? Someone? Antiderivative of x. So it's going to be x something.
2x
X
squared.
what now? Lance?
Is it 2x squared?
Close, right? Add 1, so you get x squared.
Oh, 1/2.
1/2
Oh,
x
yeah, and then you have a 2 in the bottom, right? Okay, divide by 2. Don't multiply by 2, but divide by 2, right? Now, what happens? The minus 3 is going to stay here. What happens with x to the minus 2? What does that give you? What does the anti-power rule give you there? That would be x to what power? What's minus 2 plus 1?
minus 1.
Minus 1, and divide by minus 1. And then add the constant. So we get x squared over 2. Notice here, the minus 3 and the minus 1, they're going to cancel each other. So you'll get plus 3. And then x to the minus 1, well, that's 1 over x, right? So it looks like at the end here, I have x squared over 2 plus 3 over x plus a constant. There's my antiderivative. Wow, I didn't expect that. From this expression, this is what I wound up with as the antiderivative. Sometimes these antiderivatives can come out looking not at all like you would think, all right? But you can always check them, right? By taking the derivative here, take the derivative and see if ultimately, it may take a little bit of simplification, ultimately, if you take the derivative of this, will you end up with x cubed minus 3 over x squared, okay? I hope we will, all right? I hope we did that correctly. All right, so there's a big lesson here. Remember, if you have the antiderivative of a sum or a difference, not a product, sum or a difference, you can break that up as the sum or the difference of the antiderivatives. So it's really, in a way, it's really easy to integrate sums or differences because you can just break them up into separate antiderivatives. Let's take a look at that again, because this happens in this next problem. Now, this one looks terrible. So you're thinking, I have no idea what the antiderivative of this function is. 2 secant squared x plus x. But if we sort of chip it apart, we'll see not that bad. Actually, pretty easy, okay? Because first, this is a sum, right? So you can break that up into 2 separate antiderivatives. Sometimes you don't have to do this. By the way, I need to write 2 dx's here. So sometimes now you really don't have to do this on paper. You can sort of do this just in your head, okay? So you can think, okay, I've got the antiderivative of sum, so I'll take an antiderivative of this one, and I'll take the antiderivative of this one, right? So I'm just going to take the antiderivative in sequence. What you're really doing is breaking it up into 2 antiderivatives, but you don't always have to write that down explicitly, okay? You can sort of just do that in your mind. Now, here the 2 is kind of in my way, right? But that's a constant. So remember constants? I can factor them in front of the integral sign, right? So here I have 2 times the antiderivative of secant squared x plus, let's go ahead and do this antiderivative. What is the antiderivative of x? That's a power of x. We just did that a moment ago, didn't we? Here we had antiderivative of x, right? What did we end up with? I think it was x squared over 2, right? So we can automatically already write down the answer here, x squared over 2, plus the, don't forget the constant that's going to show up here right at the end. So this is all I have left to finish, right? What is the antiderivative of secant squared? Don't forget the 2 is still going to be there, but what's the antiderivative of secant squared? Now, that's a trig function, so that looks you know, like it might be hard, but so we just have to think a little bit. Do we know a trig function whose derivative is secant squared? I do, but I hope you memorized it. Okay, so what trig function has antiderivative secant squared?
Tangent.
Tangent, perfect. Yeah, Van, it's tangent. So if you've been memorizing your derivatives of trig functions, what you really need to do, you'll recall that the derivative of tangent is secant squared. So that means the antiderivative of secant squared is tangent. Now, don't forget, it's multiplied by 2. You have to keep the 2 there. And then, of course, you've got this second term, x squared over 2 plus your constant. That's it. Okay, so we got rid of all of the integral signs, right? When we get rid of all the integral signs, then we have the antiderivative. So you can check this now, differentiate this expression, and see if you come up with what we started with. That's so easy here. If you differentiate x squared over 2, you bring the 2 down, right? The 2's will cancel, and you'll end up with x. So it's easy to check that the derivative of x squared over 2 is x. And if you differentiate 2 times tangent of x, well, you're just going to have 2 times whatever the derivative of tangent of x is, right? Which is secant squared. So when you take the derivative of 2 tangent of x, you get 2 secant squared x. So we can sort of very quickly check that, you know, almost without writing anything down, right? Oh, we know that's got to be the right answer. So we know we found the correct antiderivative. Okay. All right, now let's recall this kind of, it's what we're doing in integration by substitution is really the same process, okay? There's just an extra step that unfortunately we have to introduce, okay? So now let's try integration by substitution. I know this is challenging. It takes a lot of practice to get this right. You probably will still be struggling with this maybe a little bit into calculus 2, okay? Because I teach calculus 2 a lot, and I have calculus 2 students that are still very fuzzy about using integration by substitution. Okay, so here we want to integrate, we want to find the antiderivative of 1 over, now not just x cubed, but here we have 1 minus 3x cubed, right? Okay, so let's think about how we would approach this problem. Be nice if this were just 1 over x cubed, right? Because if this were just 1 over x cubed, we would write that as x to the minus 3 power. That would be a power of x, and then we would be, on our way, right? So if I were integrating 1 over just x cubed, right, instead of 1 minus 3x cubed, then I would immediately just write this as x to the minus 3 power, right? And then I would just have a power of x, and then I would integrate that using the anti-power rule. Add 1 to the exponent and divide by the new exponent. Well, so this is going to be a little more complicated, but we're going to start the same way. Let's write the 1 over 1 minus 3x cubed. Let's write that as 1 minus 3x to the minus 3 power. And then we just have to, again, realize, here I have not just x to a power, but an expression involving x raised to a power. So that's one of the key things you want to recognize. If you have x raised to a power, you can integrate that using just the anti-power rule, okay? But if you have a little bit more complicated expression raised to a power, well, we're still going to integrate that using the anti-power rule, but first we have to use this substitution process. So when you see expression raised to a power, you're going to be thinking integration by substitution. Now, you might be wrong, because integration is a trial and error process. It doesn't always, what you think is going to work doesn't always work. That's what makes integration challenging, okay? So integration much harder than differentiation. Differentiation is pretty cut and dried once you learn your differentiation rules, okay? So you can become very expert at differentiation really fast, but integration is not so cut and dried, okay? So it takes a lot more practice to become skilled at integration, and even with a lot of practice, you will still encounter many integration problems that are going to be, you're not going to be able to do them, okay? All right, and that's not just for you as a student, that's for trained mathematicians as well, all right, okay? So this is a much more challenging process, but first thing you want to recognize here is, I have an expression raised to a power. When I have that situation, then substitution might work. All right, so how did the substitution game work last time? We're going to pick a new variable. Our favorite is u, but you can use any variable that you want. Probably not y. That's probably not a wise choice. But any other variable that you like. Frequently, we'll use z as well, all right? But our favorite one here is u. And I'm going to let u represent that entire expression, 1 minus 3x. So let me write this down. I'm going to let that be 1 minus 3x. Now, what's the advantage of doing this? Because when you substitute u for 1 minus 3x, notice you get here u, instead of 1 minus 3x, to the minus 3 power. That is just a power of the variable, right? Okay. And so that is identical, except the variable is different. That's identical to integrating x to the minus 3 power, right? Okay. Except it's u to the minus 3 power, but that's just a name change, right? Okay. So now we've made this ugly looking problem into a much simpler looking integration problem. That's the point of doing the substitution. Except we have one little unfortunate complication here, right? and that is that blasted dx. The dx is still here, even when I substitute a u for 1 minus 3x. Here, I still have dx. I can't have the dx there because now I've got mixed variables in my integrand. Okay, so you've got to, if you get rid of the 1 minus 3x, you've also got to get rid of the dx. Now, you can't just erase that, okay? You've got to do that in a proper way, all right? So this is the part of substitution that students often get hung up on, all right? Van, do you recall what game we played last time to get rid of the dx? We look at this, and what do? We look at the substitution. You recall what we did, Van? Poor Van, I'm picking on Van. Does someone else remember what did we do here that was going to allow us to eliminate that dx?
I can't really recall it right now.
Yeah, okay, right. Yeah, see, I thought y'all would forget that because that's the part that everyone always forgets, right?
We just take the derivative of u, right?
Yeah, you take the derivative of u with respect to x, all right? You take the derivative of u with respect to x. Now, you could write that down, Lance, as u prime, okay? But here's where the old-fashioned notation really comes in handy. So I'm going to write that as du over dx instead of writing it as u prime, okay? And, well, Lance, what is that? That's not hard.
Yeah, it's just -3.
Yeah, it's just -3, that's right, okay? So it's just -3. Now solve this equation for dx. Solve this equation for dx. So multiply both sides by dx, and we get well, du equals -3 dx. And now divide both sides by -3. So I'm trying to solve for dx. So I get dx equal du over -3. And that's what I'm going to plug in for dx right here, okay? Du over -3. So I get here, just kind of a historical note here. It was not, this is not Newton that I think learned this trick. I think this is a mathematician named Leibniz, who was French or worked in France, and he's also one of the founders of calculus. In fact, there was a big dispute between Newton and Leibniz as to who was really the father of calculus at the time. It was a pretty bitter dispute, actually, and went on for a long time, but now it's sort of settled in Newton's favor. But Leibniz did contribute a lot, and this is, I think, one of the things he contributed. So we have here now the antiderivative of u to the -3, and then times du over -3. And see, now you don't have any x's, so now we're kind of in a lot better shape here, right? Except I've run out of space. So let me continue over here on the left. All right, Lance, now, so I have a u to a power, and I have the du. So see, that's like x to the -3 dx. Then I have u to the -3 du. So I'm gonna know how to integrate that. What is a little bit ugly here is this -3 that's hanging around. So I really want to get rid of that because that's just that's just in my way. And fortunately, that's a constant though, Lance. So how can I get rid of that constant? I can't just erase it, but what can I do with it to sort of
You can put it in front of the integral.
Yeah, it's a constant, so you can factor it out. See, that's what the great thing about what we were just talking about earlier. Constants, you can factor them outside of integrals, not variables, but constants you can. So this -3 I can factor out. Now this is not really -3. This is over -3, right? So
yeah, 1 over -3, right?
Yeah. So what you're really factoring out is -1/3, not -3, but -1/3, and then you have u to the -3 du. Wow, so easy now, because this is just a power of the variable. So now I know that's going to integrate what? U to the -2 over minus 2, right? Add 1 to the exponent. Minus 3 plus 1 is minus 2. Don't write minus 4 there. It's minus 2 because we're adding. And then divided by the new exponent, which is minus 2, right? Plus a constant. So the integral now is gone. See, so we've done the integration. That's a relief. Let's see, what is this? Minus 1/3, and then the multiply by the minus 2. So the minus is canceled. So it looks like we get something like u to the minus 2 over 6, right? Plus a constant. Now, but the last thing is, remember, I didn't start with the variable u, right? I started with the variable x. So we have to clean up our substitution because I've got to get back to x's because that's what I started with. But that's easy because u was 1 minus 3x, right? So wherever I see u, I'm just going to convert that back to 1 minus 3x. So I have 1 minus 3x to the minus 2 over 6 plus a constant. And so really that's good enough. That really is the answer. But if you want to here, you can go ahead and bring that minus 2 exponent back to the denominator. So I would have 1 over 6 times 1 minus 3x squared plus a constant. Wow. If you can really do that integration by substitution, you will be, that's really very good, okay? Because I can tell you there are lots of Calculus 2 students that really have difficulty with, would really have difficulty with this integration, all right? So, if you can do this successfully on the homework or on the sample test, right? Okay, even though it may take you a little while, then you've really made an achievement there. All right. Let's try one more before we take a quick break here, and then I'm gonna give you a couple that I'm gonna ask you questions of. All right. So now this one looks terrible because this is not just power of x because it's got this trig function in it, right? Okay, so so that's a little bit scary, and so some students will look at this and they'll say, there's no way I can do that, and I'll quit. Please don't do that. Okay. All right. So so we're not going to use the power rule here. All right. We're not going to use the power rule. This is the other situation that you want to be keen to or aware of when you're doing these antiderivative problems. Here I have a trig function, right? Sine, but it's not just x, okay? It's an expression involving x, So that's the other sort of situation you want to be paying attention to where integration by substitution can help you. So if this were just sine of x, that would be something hopefully simpler, right? But here we have sine of an expression involving x squared, something worse than x, right? More complicated than just x. So when you see that, a trig function, and it's an expression, and the expression is not just x, you want to be thinking of, integration by substitution. That might help me here, all right? All right, so, and how will the substitution work? Exactly like before. We're going to let u be equal to x squared so that I can have sine of not something squared, but just this variable raised to the first power. So I'm going to let u be equal to x squared. And things start off very swimmingly here. You get x times sine of, now x squared is u, right? So I've just got sine of u instead of sine of x squared. So that looks all better, right? But now I look at this integrand and I'm thinking, well, okay, that I got rid of the x squared, but I still have this x hanging around. I can't have that because I've got mixed variables, and even worse, I've got the dx hanging around, right? I cannot have that. I've got to get, if I'm going to change from x to u, I've got to change all the x's to u's, right? So how in the world do I do that? That's the second step of this process. Take the derivative of u with respect to x. So what is the derivative of x? squared, guys. Someone typing that for me or just saying it for me. Yeah, what's the derivative of x squared? 2x, sure, right, Donna, 2x, okay? So we know that du dx is equal to 2x. Now solve this equation for dx. And when you do that, you will get dx equals du over 2x, okay? All right, so I'm skipping some steps there, but that's what we end up with. And now that's what we're going to substitute for the dx, right? Notice the x isn't gone yet, though. But hopefully something nice will happen. So I have now sine u times dx, but dx is du over 2x. And here's the nice thing that happens here. So we get really lucky, thank God, all right? Notice the x's divide out. So that pesky x is gone. The 2 isn't gone, but the x is gone, right? And the x is what was really troublesome to me because the constant now I can deal with. How can you get rid of the constant? So what do we do up here with the -3?
Bring it out front.
What now? Bring it out in front. Yeah, bring it out in front. Since you're really dividing by 2 here, Van, what you're bringing out in front is 1/2. So factor out a 1/2, and you have any derivative of. Now you just have sine u du, and now that you can figure out just by inspection what function's derivative is going to be sine u. Don't forget the 1/2 is going to be there, right? Okay, so now you just ask yourself, what function gives me derivative sine u? What is that?
Negative cosine u.
Yeah, it's something like cosine u, right? But it's not quite cosine u, because if you take the derivative of cosine of u, right, you get minus sine of u, right? So you have to fix this by putting a minus sign in front, right? So when you take the derivative of minus cosine, you get positive sine. And then don't forget your constant. And now all you have to do here now to fix this is undo your substitution. So you have cosine of x squared now, because u was x squared there, plus a constant. So finally, there's the answer there, right? There, it was not a bad answer at all. There's the antiderivative. So apparently, if we I think it's pretty easy to check this. If you differentiate minus 1/2 cosine of x squared, you will get x times sine positive x times sine of x squared. All right. Well, we have to do some more examples with integration by substitution. So I've got some more, but I'm going to let you help me with these so that you will know so that you'll get a little bit better practice with these steps. Okay. All right. Before you have to try it on your, before you have to try it on the homework, or even worse, on the test, right? Okay. All right. So let's take a few minutes here. We'll come back at 12:40 and work some more on integration by substitution. Now, the good thing is, just to give you a little pep talk here, the good thing is we do have one more application of integration to look at on Tuesday, but once we've done integration by substitution, the applications are really straightforward. All right. Because well, they're straightforward, right? The really challenging thing is practicing the integration, and in particular the integration by substitution where that's required, but that's not always required. Okay, so don't think every problem is going to involve integration. Every integration problem is not going to involve integration by substitution. All right, so let me pause here and then we'll come back at okay, guys, we're back. So everyone come back together here because we're going to I want y'all to work with me on these. And so I'm going to ask y'all maybe questions about these, right? So be paying attention. So so you can respond to me if I ask you questions about them. So if I try to embarrass you or something, you won't fall for it, right? Okay. All right. So let me start this one though before I let y'all think about it. So clearly we have a pretty complicated integrand here, right? Sine squared 3x times cosine of 3x, right? So that's a complicated function to integrate, to find the antiderivative of, obviously. I'm going to rewrite it slightly just to make it easier to ponder here how we should proceed. Let's rewrite the sine squared 3x. What that really means, of course, is sine of 3x, that whole quantity squared, right? Times cosine of 3x. So I think it's easier to think about it if this sine squared 3x is written like this, okay? The reason I think that's easier is I think obviously looking at this, right, we probably want to try some sort of integration by substitution because this is a pretty complicated integrand. And but the question we want to ask ourselves is, you know, what substitution should we make? So remember, there are two situations you're looking for, right, that can kind of prompt you in thinking of what would be an appropriate value for you to substitute, right, into your integrand. And so, but there are two things that that both of those situations are occurring in this problem. So remember I said, if you have an expression raised to a power, not just x raised to a power, but an expression raised to a power, that is a good opportunity often for substitution. And see, that's exactly what we have here. We have sine of x, this, not just x, but sine, actually it's 3x, right? So instead of having just x raised to a power, x squared, we have this expression sine of 3x raised to a power. So it looks like this could be a possible substitution here. Substitute u for sine of 3x. So that's an available option. But remember also, if you have a trig function of an expression, then that's another situation where you often can use integration by substitution. And that also is happening in this integrand because you have a trig function, like for instance, cosine, right, of an expression, not just x, but in this instance, it's 3x, right? So another possible substitution that we might be thinking about is let the u equal to 3x because we have this trig function applied to this expression 3x. So it looks like we have maybe two different ways we can go here. So the question is, you know, which way should we go? Well, you know, well, sometimes you don't know in advance, you know, which choice to make. So sometimes in integration, you have to just do some trial and error. You just have to try something and then see what happens. And if, you know, if that works out good, then great. But if it doesn't work out, then maybe go back and, you know, go with your plan B, right? So let's just make a choice here and try it. And if it works, then that's fine. And if it doesn't work, then we'll try something else. Okay. So, so let's try this substitution. The first one that I looked at where I was thinking, let's let u be sine of 3x. Okay. So let's let u be sine of 3x. And that's what, so I'll forget about this substitution. And that's what we're going to try to substitute here into my integrand. So instead of writing 3x here, I will write u. So I'll have u squared instead of sine of 3x squared. But don't forget now, I still have cosine of 3x. That hasn't gone anywhere. And then the dx. So this part now I have to somehow try to eliminate, right? or I have to somehow try to rewrite these x's so that they involve u. And of course, you're going to do that by taking the derivative of u here, right, with respect to x. So that's the key. Once you've made the substitution, that's the key second step here, right, is take the derivative of u with respect to x. All right, and then continue your substitution once you've calculated that. All right, so I want y'all to try that for me. Try finding du dx. So try finding the derivative of sine of 3x. I know you know how to do that, really easy. And then remember, you're going to solve for dx and then try to substitute for dx into the integrand. So try that and see what you come up with. You don't have to finish the integration. Just see if you can finish the substitution and then tell me if it, does that simplify nicely? Because if that simplifies nicely, then we probably made the right substitution choice. But if it doesn't simplify nicely, then we'll be back to the drawing board. All right, so continue from here with computing du dx, and then try to substitute for dx and see what you get. So I'm going to give you 2 or 3 minutes there to try that. And then I'm going to ask someone. Okay, this is getting exciting. So this is exciting. So I'm getting impatient here. So I'm going to ask someone. Zachary, are you there? Zachary? Don't worry, I'm going to ask you easy questions. So Zachary, are you there? All right, Zachary. So can you tell me what is the derivative of u? What's the derivative of sine of 3x? Because that's the first thing that we needed to find here. So what's derivative of sine of 3x? Perfect. Gosh, I thought I was going to be able to catch you on that one, but you outsmarted me. Right. So sine of 3x is just 3 times the cosine of 3x, right? So that's the very first thing, is find this derivative. And then, Zachary, we have to solve this equation for dx. So did you solve that equation for dx? If you solve this equation for dx, treat dx like it's you know, an individual object, and solve for dx. What do you get out of that when you solve this equation for the dx? All right, so Mohammed, are you there? Did you solve the? Can you solve this for dx to help Zachary there with solving for dx? Mohammed, are you there?
Yes, sir. Yes, sir.
Yeah. So Mohammed, we want to solve this equation: du over dx equal 3 cosine 3x. We want to solve that for dx. Okay. So
Yeah.
how would you solve that for dx?
Uh,
What could you do first
So-
there?
we 3 cosine 3x. 1 second, my screen is not working.
Oh, okay. All right. So we have. So you can't see that.
Oh, so we differentiate the cosec, so it comes out to minus sine x.
No,
And
no,
we
we don't want to.
multiply
No, we don't want to differentiate. We already differentiated sine of 3x. So we got
Oh.
du over dx is 3 cosine 3x.
Yes.
And now we just want to solve for the dx.
Oh,
Because I want to get rid of dx over here. So I want to solve this equation for dx so that I can get rid of the dx over here. All right.
okay.
So what would be the first step in solving that equation for dx? Malcolm, do you know that? What would be the first thing we would do to solve this equation for dx? Because I've got to get it as dx equals something.
So to take out dx, I think we gotta multiply with dx by something.
Yeah, multiply both sides by dx.
Yes.
Multiply both sides by dx. Okay. So multiply both sides by dx. And then here the dx's cancel. So you get du is equal to 3. The right-hand side gets a little bit messy temporarily. So you get 3 cosine 3x times dx.
Yes.
And now, how do you finish solving for just dx? Because you want dx by itself. So how do you finish solving for the dx there?
Then divided by
Divided by what?
cosec.
What now?
3 cosecs or both sides, right?
Yeah, divide both sides by 3 cosine 3x, right? You just got to get rid of this, right? So divide both sides by 3 cosine 3x, perfect. And then that gives you, these divide out, right?
Yeah.
So you get dx equal to du over 3 cosine 3x. And that's what you're going to plug in for dx up here. All right, so let's do that. So we have u squared cosine of 3x, that hasn't gone anywhere yet, times then this big mess that we have for dx, right, which is du over 3 cosine of 3x, Mohammed.
Yeah.
Yeah, now good things are happening to us because things are going to cancel, right? What cancels? Can you see this?
Cos 3x. Yes.
Yeah, the cosine of 3x is canceled, right? Not the 3 yet, okay? And so that's very fortunate. We get a really good break that the cosine goes away. So notice what's left is nothing but a bunch of u's plus this 3 in the denominator, right? So how can I get rid of that?
By putting in 3x in the equation, in the u squared, or
No, you're making it too complicated. See, here, dividing by 3, that's a constant. But what do we talk about? Constants in front of integrands, what can we do? Lewis, are you there? What can we do with that 3?
I have no idea.
Yeah. We've done it a couple of times, right? Okay, already. So you do have an idea. Let me remind you. All right. So for instance, here, Lewis, we had this almost the same situation. Can you see this up here where I had du over 2, right?
Yes.
Are you looking at that?
Yes.
Yeah. So how did I get rid of the 2 there? When I moved from this line to this line, what did I do?
You find the derivative?
No, right. No, I'm not finding derivative. This is just algebra. I had this du over 2, but notice down here it's just du. It's not du over 2. What happened to the 2 is what I'm asking. What did I do with the 2? I didn't erase it. Where did I put it? In moving from this line to this line, where did the 2 move to? See, here it's there. Where is it down here?
The half?
It's the 1/2. Yeah, it's this. Okay. See, this is really 1/2. I don't have the 1 written up here, right? Okay. So here I have the 1/2 inside the integrand, right? Behind the integral sign. But here, Lewis, where is it?
Behind the 1/2?
No, this is the 1/2. See, I have the 1/2 here behind the integral sign, but now here I have the 1/2 where? It's not behind the integral sign anymore. Where is it?
In front?
It's in front, right? I'm going to factor the 1/2 in front of the integral sign. See, that's what we discussed earlier, right? That's a nice thing about integration is constants. You can factor them in front of integral signs. So this 1/2 that was inside the integral, I can pull it outside the integral. That's exactly what I'm going to do here. Okay. This is not a 1/2 now. This is a 1/3. It's really the same as 1/3. You don't see the 1 there, but I can write it in there. See, there's a 1/3, right? It's inside the integral. So where can I move it?
In front of the integral?
In front, right? Yeah. Okay. So there's a very important lesson for you there. The integral I can move in the 1/3 I can move in front of the integral sign. And now, Lewis, I'm left with just u squared du to integrate, right? The 1/3 is going to hang around, but what I'm really focusing on is integrating u squared du. But that's just a power of u, Lewis. So I know how to integrate that. I integrate that using the anti-power rule. So what's the integral of u squared? So what's the trick there? What do I do with the power?
Move the 2 to the front?
No, that's differentiating. I'm integrating. So I'm doing the opposite, right? I don't bring the 2 in front. That's differentiating. This is anti-differentiating. So what do I do with the 2 in that case?
You add 1 to the
Add
x.
1, right, Lewis? Think
Yes,
about that, right? Yeah, it's add 1. So you get 3 and then divide by 3. All right. So you're going backwards here, right? Remember, this means anti-differentiation, not differentiation. And then now you have to add on your constant. That's just a formality. So here I get u cubed over 9, because 3 times 3 is 9, plus the constant. Now I have to remember, now I have to remind myself, what was u? Oh, it was sine of 3x. So what I really have here is sine of 3x cubed over 9 plus the constant. There's your final anti-derivative, Lewis. This is anti-derivative, not derivative, but anti-derivative, opposite of derivative. Okay. So don't forget that this step, right? The 1/3 that's in here, I can bring it in front. So I can move it out of my way so I don't have to deal with it. And now I get a very easy expression here to find the antiderivative of. All right, let's try another one. Okay, so that was very informative, right? Because I can see what I expected, where y'all are getting hung up on. All right, but that's fine. All right, we'll get past that. Let's look at this one, and let's see if we can try this one. This one's terrible. See, okay, right, because you have x cubed plus 1 to the 5th power, just a nasty expression, and then even worse, in front here you have x squared. What are we going to do with that? Okay, so that's not one that's just going to be a simple application of the anti-power rule, right? But again, what is kind of what is it that we kind of want to see here, right? What is it that we kind of want to look at? What do we want to catch our attention in this integrand? Okay. See, I'm thinking this is really complicated, so I probably need to use integration by substitution. Maybe I'm wrong, but probably that's what I want to try here, right? And so what's going to be catching my attention here that would sort of prompt me on what substitution that I should use? Anybody want to explain that to me? What should we really be focusing on in this integrand? What sort of key fact about this integrand should be really popping out at us?
The variable inside the parentheses.
What now? The what?
The x cubed plus 1, the one inside the parentheses.
Yeah, so we have the x cubed plus 1 van. What about the x cubed plus 1? It's the fact that we have x cubed plus 1 what?
An expression raised to a power.
Oh, Donna, you said that so beautifully. Yeah, that's exactly what I'm hoping is running through people's heads. Okay, so I know it's probably a little bit fuzzier than that, but Donna said it perfectly. We have an expression raised to a power, right? So it's not just x raised to a power. If this were just x to the 5th power, that would, probably be a lot easier, right? But I have this expression raised to a power, right? And so I'm thinking I'd like to have just a variable raised to a power, not a whole expression raised to a power. Maybe if I just have a single variable raised to a power, I can integrate that using the anti-power rule, right? Okay, but here I have, unfortunately, x cubed plus 1 raised to a power, but I'm just going to remedy that by substitution, you see. Okay, so it looks like that the correct substitution would be let u be x cubed plus 1. Okay, let u be x cubed plus 1. So now maybe I'm not right there. Okay, so we often make mistakes in integration and strategic mistakes in integration, not just silly mistakes. So maybe I've chosen the wrong strategy here, but the only way to know that is to try it. Okay, so let's let u be x cubed plus 1. Okay, and now let's go through the process. Okay, so y'all guys help me I'm not going to write it down, but you guys help me just remember what is the process. Once I've decided what the substitution is, what's the first thing I do? Someone tell me there. So once you've decided that u is going to be x cubed plus 1, then what's the next thing that you do?
Rewrite it.
So Van, what?
To rewrite the problem and then find the dx.
Oh, I see. So you're saying rewrite the problem. So I'm going to have this as x squared times u to the 5th power, because I'm going to write u instead of x cubed plus 1, right? Okay, so that's fine. And then the next thing you said was what?
Find the dx.
I have to get rid of the dx, right? So I've got to find what I need to substitute for dx. And how do you find that? What you substitute for dx?
Find the derivative of u.
Find the derivative of u, right, with respect to x. So once we've written u equal x cubed plus 1, let's find du dx. That's pretty easy. What is du dx? So what is the derivative of x cubed plus 1?
3x squared.
3x squared. So write that down and now solve this equation for dx. You do that by multiplying both sides by dx and then dividing by 3x squared. So you end up getting dx equals du over 3x squared. Once you've done this a few times, solve for dx, that becomes sort of automatic. So you hardly have to think about it. You're going to get du equal, you're going to get dx equal du over 3x squared. And now that is what you substitute. So you have x squared u to the 5th power, and then dx is du over 3x squared. And now nice things happen here, right? So this is what we were hoping for. This is what we were sincerely wishing would happen. The x squares will cancel, because if they don't cancel, there's not a lot you can do here, right? So you're sort of stuck. So the x squares cancel. I'm left with this 3, but that's no problem. That's no problem, right, Damien? Because what am I going to do with the 3? So you answered this before, so your same answer still applies. What do I do with the 3 there?
Move it.
Move it, right. Move it where?
To the front.
To the front. So what am I going to have in front here?
3.
Not 3, because this is over 3, right? So so I don't get 3 in front, but what do I get in front?
Oh, 1/3.
1/3, right. So I have 1/3 antiderivative of u to the 5th power du. And now that's a very easy antiderivative because it's just a power of u. So it's not this complicated power, right? Okay, it's just a simple power of u. And I know by the anti-power rule, that's going to be u to the 6th power over 6, right? Just add 1 to the exponent and divide by the new exponent, and then add on that constant. So I end up here with, looks like u to the 6th power over 18 plus this constant. And but u was x cubed plus 1. So instead of writing u, I'll write x cubed plus 1 to the 6th power over 18 plus the constant. So there it is. There is the antiderivative. So that looked terrible, but it actually has not a bad antiderivative at all. Okay, it's pretty easy to find. All right, let me show you one. We're going to finish with one more example. And sometimes integration by substitution goes awry, and here's one case where where that happens. All right, so I saved this problem to illustrate this. All right, so now I have t instead of x, but that's okay, right? So when I'm looking at this problem, I'm going to think, I have an expression raised to a power, right? This is not just t raised to a power. This is 5t squared plus 1 raised to a power. So so that looks like a good opportunity for substitution. So you may be thinking, okay, I'm going to let u be equal to 5t squared plus 1. And then let's take the derivative of that, and that's all goes very easily. The derivative here is 10t, because the derivative of 5t squared is 10t. And then we solve this for dt now. Instead of dx, we solve for dt. So we have dt equals du over 10t. All right, so that all seems very nice. I'm going to plug that in for the dt there. So I have antiderivative of u squared. What could be easier, right? Okay, so that seems like that's working out very beautifully. And then I have, for my dt, I have du over, and darn it, here's where things go awry. I have du over 10t, because that's what dt is equal to. Now, the over 10, I can deal with that, because I can just bring out in front a 1/10. So I can get rid of the 10, but the t is not going anywhere, right? Because there's nothing to cancel with the t. So I get stuck here because I've got these two variables, u and t, and I need just one variable, and there's nothing to cancel the t. So the moral of the story here is that this substitution just didn't work, all right? Sometimes integration by substitution is not the right strategy, all right? So here's a case where it falls apart. So that happens, all right? That's life. Now, that doesn't mean that we cannot find this integrand. We cannot find this integral, though. Here's what we can do. We can resort to plan B here, because the 5t squared plus 1 squared, this is not a very high exponent, all right? Fortunately, that's not a 10th power or a 5th power. That's only a square. And so I can just expand that product. I can take 5t squared plus 1 and just multiply it by itself. That's the same as squaring it, right? So I can just actually expand this square by multiplying 5t squared plus 1 times 5t squared plus 1. And that ends up being, once you go through the algebra, that ends up being 25t to the 4th power plus 10t squared plus 1. So I can write my integrand as 25t to the 4th power plus 10t squared plus 1 dt. Now this you can integrate just one term at a time. So because you see you've got a sum here, right? So remember, when you have integral of a sum, you can just integrate each term separately. So I can integrate 25t to the 4th power. I can just use the any power rule. So that would be 25t to the 5th power over 5. Just add 1 to the exponent and divide by the new exponent. Here, same thing. 10t squared, I can just integrate that. That would be 10t cubed over 3. So I can just integrate that. And then 1 is easy to integrate. The antiderivative of 1 is going to be just t, because the derivative of t is 1. So you can integrate this one. You just get lucky here because this power is not very large. So you can just expand that power to get rid of the exponent, just square 5t squared plus 1. And then you can just integrate using the any power rule each one of these terms. So you really didn't need a fancy substitution here for this antiderivative. Okay, in fact, the substitution in this case doesn't work. All right, so I think in your homework you may have some integrands where you're just squaring an expression like this one. So you might try integrating that just by expanding the product. Go ahead and square the expression. You don't have to do integration by substitution in that case. But now if this were a little bit higher power, like 4th or 5th power, it's very hard to expand 5t squared plus 1 to the 5th power. So you could do it if you had enough time, but that would be hard. And so I don't know, that would be just a much more difficult thing to integrate. Okay, all right, well, we run ourselves out of time. So but that's the end of my examples of integration by substitutions in any case. All right. So so don't forget, the answers to the sample 3 will be posted sometime later today. So I will send an email when I get done with that. And then the video for sample 3 will be sometime tomorrow. I will post that. So that will be posted on Blackboard, right? So be looking for that. And so and I think it's really good to watch that, because that may give you some ideas of what to focus on for test number 3 from that sample test. And then don't forget, on Monday, Madison will have her test review. So I strongly encourage you to go to Madison's test review for test number 3, since we don't have a lot of time, right? Okay, so I know that will be very helpful to you in preparing for test number 3. And then we will have class on Tuesday, right? And then after class, as usual, that's when the test will that's when the test will be posted, and then it'll be due on Thursday. Okay, all right, so that's all I have to say today. Yeah, if you have any questions, you can ask me questions. All right, any questions?
Do we have class on Thursday next week?
No, there's no. So our schedule will be our class schedule will be Tuesday, and then that's it. And then the following week on Tuesday, the 11th, is the that's the final exam time period. But we don't have class during the final exam time period. So, but I probably will go ahead and be available on Zoom at that time, so that if you have any questions you want to ask me. Since we have so little time to ask questions, if you want to ask me questions at that time, you can, but we won't have a lecture on that day.
Okay. Sounds good. Thank you.
Okay. Anything else?
And you will be posting a final exam review later on, right?
There will be a final exam review. There will be one posted. And then Madison will also have a final exam review session, but there will be a final exam review sheet posted, and I'll talk about that on next Tuesday. That one has there are questions, and then there are solutions to that, and each solution has a video that goes with it. So those have already been filmed. So so you have a nice final exam. There's a nice final exam review.
Okay.
Okay.
Thank you, guys. Have a good weekend.
All right.